Hi everyone, this is Jude, and for this project, I used Newton's law of cooling to figure out how fast water cools down in different types of cups. Before getting into the experiment, here's the main idea. Newton's law of cooling is basically saying the hotter something is compared to the room it's in, the faster it cools off. That's what I used to model how the temperature changes over time in my experiment. This is the differential equations that we started with, and we had T sub t for temperature at time t, and A for the ambient temperature, and K, which is what I'll be solving for later, which is the cooling constant. Now I'll show you how I set up the experiment and I collected the data. Before I do that, here's the step by step of what I did. I heated up water, poured it exactly 1 cup into each cup, uh, and then I used a thermometer to measure the temperature every 15 minutes until I hit 45 minutes of total. I then took those data that I got for the temperature, put them in a table, and used that data to solve for K, put those K values in a table, compare them, and then I also did the exponential cooling behavioral graphs. So we'll get into that in the next slide. For the materials I used and the setup, I had a plastic cup, a glass cup, and the insulated coffee cup. Thermometer, I used a different one later on in my experiment because this one was in degrees Celsius and I needed Fahrenheit. And I also used this timer to time out the 15 minutes at a time for each of those timestamps. Now, for the data, after getting all the results, this is the temperatures I recorded. You can already see how each cup cools down at a different rate. The coffee cup stayed hotter longer, and the glass cup dropped the fastest to 97 degrees Fahrenheit, where the plastic cup was kind of in the medium of the coffee and the glass cup. Now let's look at the graph so it's easier to compare. You see right here the yellow line is the coffee cup and the blue line is the plastic and the red one is the glass one. And in here I have those results in Desmos. You can really see the differences here. The glass cup drops down pretty fast, where the plastic one is kind of in the middle, and the insulated cup holds the heats the best, which is the most like flattest one. So in this page, I solve for k. This is the general solution, and I rearrange this general solution so that I can solve for k. And this is what we get at the end: 1 over t natural log of t sub t minus a, t sub 0 minus a equals k. For the plastic cup, all I did is basically plug in this value, this value, this value, and this value, which these bottom two values are the same for all of them since all of them started at the same temperature and all of them have the same room temperature. Only the top number changes up here, where what temperature was after 15 minutes. As you can see right here, we have 1 over 15. That's what the equation right here tells you to do. 1 over time, which is 1 over 15. And I did that for all of them and I got the results. So as you can see here, the plastic cup had a negative 0.038 and the glass one had negative 0.0510 and so on. So the coffee one had the smallest number of all, which means it cools down the slowest of all. After calculating all of that and getting those results, I compared those values and I put them in a table. As you can see, the glass one is the fastest cooling, the plastic is the medium cooling, and the insulated cups, just like we discussed earlier, is the slowest cooling one, and which is the best one. So, for conclusion, Newton's law of cooling actually uh, modeled the temperature change in each cup. This experiment confirmed what I expected. The more insulating the material, the slower it cools. Newton's law matched my real data really well, and this idea isn't just for experiment, it's actually used in real life. This is the same idea used in designing coffee cups, coolers, and building installations. And materials with obviously the materials with like lower thermal conductivity are better for retaining temperature. And yeah, thank you for watching.